So, good morning, everyone. Uh, s- uh, First of all, I would like to thank the organizers for giving me the opportunity to speak in such a big platform. I am Swayang Priya Mahanta. So, currently, I am doing my PhD under the supervision of Professor Subhankar Vedanta at NISER, Bhubaneswar. So, today I will be talking on the topic influence of graphene and antimony underlayers on magnetization dynamics in FeCo thin films. So this is a brief introduction. So to characterize any material, like to represent any material, depending on the coordinates, number of coordinates we need, they are classified into four categories, mostly 0D, 1D, 2D, and 3D. So in this talk, I will be focusing mostly on the 2D material. So in 2D material, what we do, like if we confine the direction along if we confine the material to stay in two directions, and then like we need two coordinates to represent it, then it is 2D. Then what are the benefits? Like because of the ultra thin nature, we get a very strong interfacial effect, and because of the high surface to volume ratio, we can basically tune several properties like the electronic as well as magnetic properties. Not only these things, when we thin down, like the properties will be much more different if we compare it to the 3D counterpart, and we can change the density of states, and hence we can control the spin orbit coupling strengths. So the question is, if we combine two different 2D material, what will happen? So we expect like it will lead to new physics and a new interesting phenomenon. So in this slide, I have listed four 2D materials like graphene. Then there are monolayer transition metal dichalcogenoids. Then another interesting thing is beta antimony. Then very famous hexagonal boron nitride, which is popularly known as HBN. In this particular work, so we will be focusing on graphene and beta phase of antimony. So, beta phase of antimony, its structure is quite similar to graphene. Graphene is a flat honeycomb-like structure. The measured antimony, it is also similar to hexagonal honeycomb-like structure, similar to graphene, but it is not flat. It is slightly buckled. Theoretically, it is predicted that layer by layer structure of graphene antimony can be synthesized very earlier, but very recently scientists are able to synthesize this 2D phase of antimony, and it opened up like really interesting scenarios for scientists to uh, to take the advantages of strong spin orbit coupling as well as the topological properties and different topological behavior which antimony shows when it is thinned down to 2D layer. So one challenge is like this 2D antimony that cannot be grown on any substrate. So one thing is observed that if we grow antimony on top of monolayer graphene, then we can stabilize the beta phase. Whereas if we take multilayer, then it is observed that no beta phase can be stabilized. So considering these aspects, like we have fabricated these four heterostructures. So kindly note that the sample 4 is quite important for us, where like we have stabilized beta phase of antimony on top of graphene. Then sample 1 to 3 are reference to the sample 4. In sample 1, we have directly fabricated the ferromagnetic film FeCo on top of substrate. In sample 2, we have taken graphene, and on top of that the magnetic FeCo layer. In structure 3, there is antimony directly on top of substrate, then ferromagnet is deposited on top of graphene, and in 4, it is graphene on which beta phase is stabilized. Then the further thing. We have used copper to cap the ferromagnetic layer. And we have fabricated these structures by collaborating with Dr. Luis Aviles Felix and Dr. Laura Serkovic Loli from Argentina. And Dr. Luis will be giving a invited talk in session 10 on FeCo dynamics of FeCo thin films. So, before characterizing the magnetic part, we have seen by performing X-ray photoemission spectroscopy measurement, we have confirmed the presence of antimony as well as graphene by doing by taking the XPS spectra. So these four figures are showing the binding energy versus the intensity curve, which confirms that like SB and the graphene films is well deposited on top of substrate, but to confirm the phase, we have to perform Raman spectroscopy. In figure 1, you can see like when antimony is deposited on top of graphene, these two EG and AG mode are the in plane and out of plane vibrational mode for antimony. Then in figure 2, these 2D G and D bands represents various modes for graphene, and the G intensity of G and D band tells that it is a monolayer graphene. And in figure 3, we have shown the Raman spectrum when antimony is directly deposited on top of silicon substrate, and you can see there is no any Raman peaks. So which tells that when SV is deposited on top of graphene only, we are stabilizing the beta phase. So from here, we are confirmed that we have the beta phase of antimony in sample 4. To check the ferromagnetic part, FeCo is usually polycrystal in nature, and we have performed X-ray diffraction measurement, and we observed the BCC 110 plane of FeCo for all the heterostructures, which tells that by taking a 2D layer below the ferromagnet, it is not affecting the crystallinity. That is, the buffer layer has very negligible impact on the crystallinity of FeCo thin films. Then, to do the magnetic characterization, we have performed inverse spinel effect. Here is a brief introduction. So here, when we place the magnetic thin films on top of coplanar waveguide in a flip chip manner, and we pass radio frequency wave through the sample, then and apply external magnetic field, then during resonance condition, what happens? Samples absorbs energy, and because of the inverse spinel effect, like we detect a transverse voltage with the help of nanovoltmeter. Now the magnetization dynamics is basically governed by the Landau-Lipschitz Gilbert equation mentioned here. Here the important factor is alpha, which represents the Gilbert damping constant. So when we take a spin sink near to a ferromagnet, what happens? The non-magnetic layer will absorb the spin angular momentum from the ferromagnet, which will be reflected as enhanced Gilbert damping constant as represented in this equation. So we have performed FMR, and in this plot we have shown the frequency versus H resonance plot, which follows this Kittel equation, and by fitting with this equation we extract the parameter gamma and use this gamma in second equation, which relates the line width to frequency to extract the Gilbert damping constant alpha. So in this table we have listed the Gilbert damping parameter for all the films, and we can see that for FeCo films the Gilbert damping constant is 0.008, which is quite similar to the values reported in literature. Now when we took the FeCo with SB as well as graphene, then we see there is an enhancement in Gilbert damping constant, which tells that both antimony and graphene acting as good spin sink, like they are absorbing a good amount of spin angular momentum from the ferromagnet. Now with the main sample, that is the graphene and beta antimony interface, we see that the alpha value has increased significantly, like from 0.008 to it has reached 0.030. So which is quite large. So this is expected because we have predicted that the beta antimony and FeCo will have a high spin orbit coupling strength interface, and that can lead to a better spin sink as compared to other thing. So to get a direct visualization, we have measured the voltage, and these plots shows the inverse spinel effect voltage of all the samples at when the magnetic field and the contact angles are at 0 degree. So in this table, we have listed the symmetric as well as anti-symmetric component of the voltage, and it is we have observed that for both the graphene and antimony interfaces, the symmetric component of the voltage has increased, which can be attributed to the spin pumping happening at the interface. However, we expected a large signal for sample 4. Unexpectedly, we are like the signal is diminished for the fourth sample. So that thing is still under investigation. One possible reason we are speculating is the opposite impact happening at these two interfaces, like the beta antimony FeCo as well as FeCo copper interfaces. Probably opposite impact is happening, which is cancelling the net voltages, which were net transverse voltage. So in summary, I can say that we have successfully synthesized the monolayer of graphene and beta antimony, and we have observed giant enhancement of Gilbert damping constant with all the 2D layers, like for graphene, antimony, and beta antimony. Then enhanced ISHE voltage for graphene as well as antimony underlayer as compared to the reference ferromagnetic FeCo layer. However, ISHE voltage is diminished where we expected to get a greater signal. So we are still investigating, and our future plan like we are planning to change the capping layer, because currently we are speculating that probably opposite impact is happening at both the interfaces. So in this context, like we are planning to change the capping layer to aluminum. And since FeCo is known to give a very strong two magnon scattering signal, we are also like chosen a different ferromagnet, which is cobalt iron boron, to get a better magnetic response, to clearly conclude about the behavior of beta antimony in phase in terms of controlling the magnetization dynamics of a ferromagnetic thin film. So I would like to acknowledge my professor, Professor Subhankar Vedanta sir, for giving me the opportunity and his continuous encouragement, as well as all my lab members for their support and help. Thank you.
Thank you for the nice talk. Let's move on to Q&A session. Does anyone have questions? Sorry. There is a question from the chat. For practical applications, Gilbert damping should be low, but here it is increasing. What will be the application of enhanced damping factor?
It is true that like for application purpose we require low damping, but that low damping basically refers to the damping constant of the reference ferromagnet. Like if you see, FeCo is a metallic ferromagnet and it is 0.008, which is quite good. So since we have taken a spin sink, like good spin sink near a ferromagnet, that is reflected as like increased alpha. So here by telling that alpha has enhanced, that means that like we have a good spin sink. So the main like the question which that person has asked, like it refers to controlling the alpha of the reference ferromagnet. So we can tune various conditions to achieve low Gilbert damping, intrinsic Gilbert damping constant of the ferromagnet.
Okay, then there is another question. How changing the capping layer to AL will help?
Okay. It will help because like there are various reports, because we have taken capping layer as copper, so the top copper is basically giving copper oxide, and copper oxide that is that can lead to give some voltage, like because of this orbital Hall effect and other things are coming into picture. Copper also contributes to like in ISHE experiment, copper oxide contributes in voltage. However, by taking aluminum, it is seen that like that doesn't give any voltage. So we are planning to take aluminum, or any other oxide can be a good choice, like SiO2. Like the main goal is to take such an interface from which we will not get any voltage. So copper definitely gives some voltage. So in that way, like we are planning to take a different capping layer.
Thank you. And there's question from audience.
Yeah.
Uh, Hi, I have one small doubt here. Can you like show me the slide where you have fitted damping?
Yes.
Yeah, here. Like I can see there is a non-linear term as your frequency is increasing from. So, are you considering any factor for that, or it is like two magnon scattering or anything? Are you just going with
Yes,
the?
it is actually two magnon scattering. So if you see any literature related to FeCo possesses very strong TMS at low frequency. So here also
So
like the yeah.
did you estimate it like the contribution of 2M like TMS, or it's just you fitted with the alpha and you got it? Because if you get very low alpha like 0. As you are stating 0.008, so we can also know that what is the contribution of 2 magnon scattering also. So did you fit it with that?
No, we have not yet done the two magnons scattering analysis yet. But like from the data, like below 11 gigahertz also, like the data was there is a decrease in the line width delta H, which
Yeah,
clearly
because I have seen the one data in that what happened in that low frequency, it is very high, and then it is start decreasing, and then it will start increasing over the. So,
yes.
are you
So
doing the
basically
similar
to
kind of?
calculate, that's why we have considered the linear range where it is increasing with the frequency. So TMS calculation, like we can look at that. But it is true that this FeCo system is having very strong two magnon scattering.
Okay, thank you.
Thank you.
So it's almost time. So please discuss the chat question in the gather town. Let's thank the speaker again.
Okay, thank you.